All right, so maybe I'll just get started because I just have some administrative stuff to go through, which is on the web anyway. But since you're here on time, you can have the treat of hearing me say it in person. So we have figured out a recitation schedule. So the recitations will start tomorrow. And you have 3 choices.
Sorry, something's rattling on the.
Oh. Thanks. Okay. All right. Thank you. So you can choose which recitation just by showing up for one of them. If it's too unbalanced, then we'll have to do something about that. But and the TAs also, each one has office hours, and those are listed on the syllabus. Okay, and the office hours are in the open space just outside of my office. So it's on G6 theta. This is that's my office. Okay, so I realized that yesterday I sort of went through a lot of basics of the course, but I didn't say anything about whether you should be taking the course or not. So just briefly, the prerequisites for the course. So the only one that's listed formally is 6042. So basically a 6042 or some equivalent mathematical background. So basically, it's good if you come into this course, knowing your way around a proof, knowing how to prove something, knowing what induction is, things like that. It's certainly helpful, if you have programming and algorithms experience. We're not going to do any actual programming in this course, but that experience is helpful. But the main thing is just some mathematical maturity. Okay, so one thing that a lot of people ask about is whether they should take 6045 or 6840, which is sort of the graduate version of this class that's taught by Professor Sipser. So there is a lot of overlap between them, but they're also different. And I'd say the main difference, besides just differences in style, is that this course has sort of less depth but more breadth. So we do a lot of stuff in this course, like cryptography and quantum computing, that's not done at all in 6840. So if you want to take like one course on theoretical computer science that will sort of maximize your exposure to things, then I'd recommend this one. 6840, has a little bit more mathematical rigor. Like they'll prove things that will be okay to hand wave in this course. And that one pretty much covers exactly the contents of Sipser's textbook, whereas in this course we'll just sort of dip in and out of it, and also do plenty of stuff that's not in the book. If you're really serious about theoretical computer science, then it would not hurt you at all to take both courses. And by the way, a 6046 has very, very little overlap with this course. A 6046 is about finding ways to do things, to solve problems, and this course is about understanding what you can't do, or understanding, let's say, what are the ultimate limitations. Okay, so they complement each other very nicely in that way, and you can take either one of them for your header, but again, it wouldn't hurt you at all to take both if you have room for it. Okay, so what I wanted to do today is do like our first real examples of models of computation, just to get our feet wet, but also see some really interesting models. So I mean, I think the maybe the most basic model of computation that there is, or the simplest one to talk about is that of circuits. Okay. All right. Maybe I'll leave this up for a little for people who are just coming in. Okay, so just Boolean logic circuits. So what's a circuit? Well, so if you've taken double E classes, you've seen circuits that have things that look like this or something like this, or I don't know exactly. Okay, but in any case, they have all these different components in them, and there's always a closed loop, right? Because the electrons have to flow all the way around in a circle. Okay, in theoretical computer science, ironically, circuits are never closed loops. Okay, that's like the one rule about them, that they have to be acyclic, not contain any cycles. Okay, so what we mean by a circuit, basically, is a sort of a network of logical operations. So where you start out with some bits that are given to you as input. Like, let's say, X, Y, and Z. And then you can do operations on them. So we have the NOT gate, for example. That just, if X is 0, then it outputs 1. And if X is 1, then it outputs 0. And there are symbols for all these things, but I'll just write the names of them because that's easier. We also have the AND gate, which outputs 1 if and only if both of the inputs are 1. Okay, and we have the OR gate, which outputs 1 if either or both of the inputs are 1, and otherwise outputs 0. Okay. We have the XOR gate, which outputs 1 if the two input bits are different, and outputs 0 if they're the same. Okay, or in other words, just outputs their sum modulo 2. Okay, and then what you're allowed to do is build up a more complicated logical operations by just stringing a bunch of these together. Okay, and feeding the output of one into the input of another. So to take an example, let's say that we wanted to compute the majority function of 3 bits, x, y, and z, meaning we just want to know, are the majority of these bits equal to 1? Okay, how could we do that using, using the gates that I listed there, using, let's say, AND or NOT gates? So I just want to know if at least 2 of the bits are 1. Yeah? Yeah, we could do it with XOR. In fact, there's a way to do it using only AND and OR gates. We don't even need anything else. Yeah. Let's see. Let's try that. Does this work? Unfortunately, I don't think so. So for example, suppose y is 1 and x and z are 0, right? Then you're going to get 1, 1, 1, even though, yeah. So, okay, but this sort of almost works. Can anyone, fix it? Yeah. Yep. Yeah, there we go. So let's say we just and x and y, and y and z, and x and z. Okay, and then we just OR all of these. So we could do that, if I just say, I just OR all of them. Now I didn't explicitly tell you that you're allowed to have an OR of three things, right? The number of inputs to a gate, by the way, we call the fan-in of the gate. Okay, so I didn't tell you that we have an OR of fan-in 3, but that doesn't actually matter. Why not? Because you can build one anyway. Okay, all you have to do is OR 2 of these ANDs, like that, and then OR the result of that with the remaining AND, right? Because the OR function is associative, right? You can just OR by, you can keep taking ORs, and and this is equivalent to just the OR of all the things. Okay, so this will represent the majority function because it just directly encodes it, right? It says, it's just sort of looking for any pair of the bits that are both 1, and as soon as it finds one of those, then then the circuit is happy, right? So okay. So we can build, of course, much more complicated things. We could build a circuit that performed binary addition onto numbers written in binary, or that multiplied them, or that ran Windows or Linux. Okay, don't worry, I'm not going to ask you to do any of those things on the P sets. Okay, but if you take in your systems courses and in computer architecture courses, you will basically learn or have learned maybe how to design adders and multipliers and things like that just by stringing a bunch of logic gates together. Okay, of course, this is the this is what's going on, in your computer at the lowest level, right? In some sense, what a transistor is it's precisely like a solid state, physical device that allows you to implement things like AND and OR and NOT gates, in a very reliable way, right? Because you can use a very, very weak current to control a much more powerful current, and and that once you have that ability, you can sort of use it to construct logic gates. Okay, so okay, but now you might still be worried about something, which is, I just listed a few specific gates, right? The AND gate, the OR gate, the NOT gate. I mean, who's to say that this is a complete list, right? I mean, even if you were able to use your transistors to build those gates, right? Why, as soon as I want to do something else, why shouldn't I need some other logic gate? So this leads us to sort of an important concept that will show up again and again in this course. Which is the concept of universality. Okay, So in this context, let's say if I give you a set of logic gates, like AND, OR, and NOT, we'll call the set universal. If by just stringing together gates in that set, we can represent any Boolean function on any number of bits. Okay, so this is just a little bit of notation, right? I mean, this means that f is a Boolean function that takes n bits as input. So its input is an element of the set 0, 1 to the n, meaning its input is a string of n bits. Okay, and its output is a bit, a 0 or 1. Okay, now it's clear that if we can, create any Boolean function with a 1-bit output, then we can also create any Boolean function with however many output bits we want, because we just, have one circuit to output the first bit, have another circuit to output the second bit, and so forth. Right, so that's the reason why we can just concentrate for simplicity on circuits that produce 1 bit as their output. Okay, and so so it's not entirely obvious a priori that there's any finite set of gates that's going to be universal, right? Okay. One thing that I always dislike in math classes is when they give you a definition and they never tell you any examples of anything that don't satisfy the definition, right? Like in elementary school, I had to memorize what's commutative, what's associative, right? But it's completely pointless if you've never seen anything that's not commutative or that's not associative. Okay, so let's see some examples of things that are not universal. Okay, just in order to see that that universality is not a trivial concept. All right, what's an example of a set of gates that's not universal? Anyone? In the sense that cannot be used to represent every function. Yeah. Just. Yeah, if we only had the identity gate. Yes, absolutely. Good example. Okay, we could only compute the identity function. All right, what's another example? Yeah. Not. Yeah, if we only have the not gate. Well, you're never going to be able to compute anything that involves more than 1 bit, right? Every bit will be its, its own island. Okay, no two will ever talk to each other. All right, what's another example? Yeah. Yeah, so and and or fails to be a universal set. What can and or not represent? Not. Yes. Yes, and what's the reason for that? Why can't they represent not? Yeah. Mm-hmm. Mm-hmm. Well, okay. I mean, you can. Okay, you're absolutely sort of grasping toward the there's a word for what you're trying to get at. The word we use is monotone. Okay, so and or are both monotone functions. Monotone means that if you change one of the inputs from 0 to 1, then that can only ever change the output from 0 to 1, right? Or it could also leave the output unaffected, right? But changing an input from 0 to 1 will never change the output from 1 to 0. Okay, that's what monotone means. Yeah. Okay. So this actually raises a good point, which is when we talk about universality. This is this is just a convention. This is a choice that we can make. Okay, but we're in this class we're going to say that constants are available for free. So, which means. You can always, even if you have a 2-bit gate, you can always get a 1-bit function by just feeding, like a 0 or a 1, into one of its input wires. Okay, you can always just fix one of the input wires to be 0 or 1, right? And then, restrict the function like that. Okay, so you could always, for example, if you had an AND gate, this will, you could represent just x itself, like that, okay, by just saying the AND of x with 1. Okay, so that's just a technicality, but good point. All right, so AND and OR are clearly both monotone functions, right? Changing. Right, they both satisfy this, and the property of being monotone, is closed under composition. So, if I take two gates that are monotone and I string them together, I still get a monotone function. Okay, and whereas the not function is clearly not monotone. Okay, so that's why this set fails to be universal. Does anyone know another set, a different set of Boolean gates that's not universal? There's basically one other interesting possibility. It's one that's already been on the board, actually. Yeah. XOR. Yeah, XOR. In fact, I can even take XOR and I can throw in the NOT gate also. Okay, XOR and NOT. This will also fail to be a universal set. What am I not able to represent using XOR and NOT gates? Anyone? Yeah, AND, for example. Okay, why can't I represent the AND function using XOR and NOT gates? Okay. Yeah. Yeah, that's true, but I'm allowed to string together a whole bunch of XOR gates, right? So I still need to say, why can I never get an AND gate, no matter how many XORs I put together? Yeah? Oh.
Is it because you can't distinguish between the AND and the AND?
So I'm not sure I understand that, but.
If you have two things going into an XOR, and then you got that, for example, it's like you can't tell whether that's both are true or both.
Yeah. Yeah. Okay. So ultimately, I want some sort of invariant. I want some property that's going to be preserved no matter how many XOR and NOT gates I string together. But which is not satisfied by the AND function. Okay. And yeah. Yeah. The property that I want here is actually linearity. Okay. Where with AND and OR preserve the function is always monotone. XOR and NOT preserve that the function is always linear. What do I mean by linear here? I actually mean linear modulo 2. Okay, so linear over the field that has two elements. Okay, so I can think of the XOR of x and y if I interpreted it algebraically as an arithmetic operation on bits. Then it's just x plus y mod 2, right? That's all it is. Okay. If I interpret not as an arithmetic operation, what's not? Anyone? 1 minus x, right? 1 minus x mod 2. In fact, it's also 1 plus x mod 2. Okay. If you're mod 2, plus and minus are the same thing. Okay. But now these are both linear functions, right? So you can compose these, like you could have the XOR of x and y and the XOR of that with z, for example. But that's just going to give you x plus y plus z, mod 2, right? You're always going to have a linear function in your input bits. No matter how many linear functions you compose, you're never going to get a quadratic function, for example. Okay, but what is and as an algebraic function, mod 2? Yeah. Yeah, exactly. Yeah. So. Okay. By the way, this correspondence between Boolean operations and algebra. This is why we call them Boolean operations in the first place, because George Boole in the 1800s, noticed this correspondence. I guess someone had to be the first to do it, right? So discoveries back then were sort of easier to make. Okay, so. All right, but so and is a degree 2 function. You're never going to get it by composing all these linear operations. Okay, an interesting fact, which maybe I'll put on pset 1, is that these are sort of the only, monotonicity and linearity are in some sense the only two ways for a collection of Boolean gates with constants available for free to fall short of being universal. Okay, so in other words, what we're saying is that and this is again a very sort of general phenomenon in computer science. Universality is sort of the rule rather than the exception, right? You actually have to work somewhat hard to avoid being universal. Okay, so without further ado, let's see why if you've got the and, or, and not gates, then this is a universal set. Okay, so remember the definition of universal is that we can use these gates to express any Boolean function on any number of bits, right? So we need to give a construction that does that, right? So which means that in order to prove this theorem, we'll have to start out with some arbitrary Boolean function on n bits. But we could also just do an example, as long as we make it completely clear that what we do in our example would generalize to any Boolean function. Okay. So sorry. So how can we represent an arbitrary Boolean function? Well, there's a general way to do it, which you may have seen before, which is called a truth table. Okay, truth table just means you list every possible every possible setting of the input bits. Then for each one, you list what output do you want. All right, well, so for example, what's the truth table of the AND function, anyone? 0, 0, 0, 1, yeah. The truth table of the OR function is 0, 1, 1, 1. Truth function of the XOR function, anyone? 0, 1, 1, 0. Yeah. Okay, so now I could make up anything that I want over here. Like let's do 0, 1, 0, 0, 0, 0, 1, 0. you know, there's a nice Boolean function. Okay, and now I have to show how to represent this, you know, arbitrary Boolean function by a circuit of and, or, and not gates. So can anyone suggest how I might go about this? Yeah.
Well, you can start by just taking each row of the truth table.
Mm-hmm. Mm-hmm. Yep. So yeah. So in fact, you know, all I can. That's exactly right. You know, but in fact, I can just look at those rows that output a 1. Okay. You know, in fact, what I can do is I can just look for you know, those. Okay. In this case, there are 2 rows of this function that lead to the output 1, right? And so basically what I'm trying to say with my circuit, right, what my circuit is yearning to express is that you know, you should output 1 if the input is this or if the input is this, and otherwise you should output 0. So how can we express that? How can we give voice to that statement? Yes. Exactly. So all I've got to do is for each of these rows that leads to a 1, I just you know, I implement a check that asks whether all the bits have the you know, have the right setting to be that input. So in this case, it's not x and not y and z. Okay, for this row down here, it's x and y and not z. Right. Okay, and again, I could implement these ands as ands of ands if I want them to have only fan in 2. Okay, and then what do I do at the end? Yep, and then I OR it. Okay, there. I just represented this function. Okay, and you know, in a way where, you know, we could clearly generalize this to any truth table of any size, right? So incidentally, one thing that, you know, will interest us a lot, although, you know, we'll only have the tools to really start to understand it later in the course, is the size of a circuit. Okay, by the size of a circuit, we just mean the number of gates in it. Okay, so this construction that we saw here, if you've got a Boolean function of n bits, what's an upper bound on the size of the circuit that this construction will produce? Well, how big is the truth table, first of all? The truth table has got 2 to the n rows in it, right? Any of which could have a 1 in it. Okay, for each of those rows, how much logic are we using to check for that row? Yeah, okay, that's you know, that's going to change things by a small factor, depending on, you know, whether we. All right, so one thing about this course is that, you know, all the habits that you've learned of like being really precise and calculating things, that all goes out the window in this course. Okay, and we're gonna, yeah, what? Yeah. Yeah. Well, so we want to know the dependence on n, right? We want to what? So okay, so what can we say? So each we want to, so what's going to concern us is asymptotics. Okay, so actually, so probably, you know, most of you have already seen O notation in 6042 or whatever, but just to refresh your memory about it, let me show you the notation that we're going to be using a lot in this course. Okay, so we'll be very interested in the growth rate of functions. So in this particular example, we'd like to know just the rough growth rate of the number of gates in the circuit as a function of n. Okay, that's what we want to know, and we don't care that much about the leading constants. I mean, we can work them out if we really want to, but mostly we're interested in what can be captured using this notation. So f of n, we say, is big O of g of n if there exist constants a and b such that f of n is at most a times g of n plus b for all n. Okay. This, by the way, this means for all. This means there exists. Okay. So what that is saying, if you unpack it, it's just saying that f of n is, grows asymptotically at most as fast as g does. Okay. So g is an asymptotic upper bound on f. Okay. So for example, we could say that n squared is big O of n cubed. Okay, this grows faster than this does. Okay, we could even say that ten n squared is big O of n squared. Okay, because we don't care about the 10, right? That can just be absorbed into this constant a here. Okay, but it is not true that n cubed is big O of n squared. Okay. We say that f of n is big omega of g of n if there exists a constant a greater than 0 and b such that f of n is greater than a g of n minus b for all n. Okay, so this is saying just the converse thing, that g is an asymptotic lower bound on f. Okay, when you go out to large enough n's, then f grows asymptotically at least as fast as g grows. Okay, and so in theoretical computer science, this kind of statement is very highly prized. We like to prove lower bounds on the complexity of things when we can. Okay. So we could make the opposite statements here. N squared is not theta of n cubed. By the way, some people, if they really want to be pedantic, they'll say n squared is contained in big O of n cubed, right? Because what the hell does it mean to set this equal to this anyway, right? This is actually a set of functions that contains this. All right, but I'm just sort of using the equal sign as a shorthand for is, right? Like if I say Bob is tall, I'm not saying that the concept of tallness coincides with the concept of Bobness, So I'm just using it to mean is. Okay, so all right, and but we could say that n cubed is omega of n squared, right? Okay. Okay, now we say that f of n is big theta of g of n if just both of these things hold. F of n is big O of g of n, and it's also big theta of g of n. Okay, so this means that f and g grow asymptotically at the same rate. Okay, that means that you have really pinned down the rate at which f grows if you can make a statement like that, a big theta statement. Okay, and then there's one last one that we sometimes like. we say f of n is little o of g of n. If for all positive a there exists a b such that f of n is at most or is less than a gn plus b for all n. Okay, so this is saying that f of n grows at asymptotically less than the rate of g of n. Okay, so it's saying that the g of n is an upper bound and it's a strict upper bound. Okay, so we could say that n squared is little o of n cubed. That's true, but 10n squared is not little o of n squared. Okay, so questions about these? All right, so we'll you know, there's nothing deep about these. We'll have a few p-set problems to nail these down, including with some slightly less obvious examples. Okay, so now we can say we are interested in the size of this circuit that's produced by this construction. What is it big O of? Okay, so in terms of big O notation, right? How does the size of the circuit grow as a function of n? Yeah. Huh? Yes, per row it's O of n, exactly. And how many rows are there? 2 to the n. Yep. So we can say that this construction produces a circuit of size 2 to the n times n. Okay, and you can see that between these two terms, this one is the heavy hitter. Okay, the other one just barely even matters. Okay, it's the 2 to the n that's really the killer here. Okay, because if n is 1,000, this is telling you that yes, this construction would theoretically work, but it will produce a circuit with more than 2 to the 1,000 gates. Okay, how big is 2 to the 1,000? It's more than 10 to the 300, right? The number of subatomic particles in the observable universe is about 10 to the 85. Okay, so this is more. If every you miniaturized your gates so that every one had one subatomic particle, right? This is a circuit that's way bigger than would fit in that part of the universe where the light has reached us since the Big Bang. Okay, that's a big circuit. Okay, so this and this is exactly the kind of issue that we're interested in complexity theory, right? That when you get an exponential growth, it blows up in your face to the point where something even if something theoretically exists, it's just a practical impossibility. So you might wonder, could there be an improved construction? Could there be a way to construct a circuit for an arbitrary Boolean function of n bits that used fewer than this number of gates? Ideally way fewer. Okay, well, we'll come back to that question. Okay, let me just observe first that we didn't in this universality construction we didn't actually need the and, or, and not gate. We can actually get rid of something and still have it be universal. What can we get rid of anyway? Yeah. Yes, either one, right? So let's argue that and not are already universal by themselves. Okay, well, to show this is another point that's going to recur, right? If you've already proved that A is thing A is universal, now you want to show that thing B is universal. Okay, it's now it's enough to show that thing B can emulate everything that thing A does. Okay, this we call an argument by reduction, right? you know, the standard joke. You know, how do you boil water, right? You know, you fill a pot with water, you put it on the stove. What if the water is already in the pot? Then what do? Well, then you dump the water out. You thereby reduce the problem to one that you already solved. Okay, so how can we reduce the problem of showing that and not are universal to one that we've already solved? Yeah. Yep. And how do we do that? Yeah. Yeah, yeah. So we say not the and of not x and not y. That's exactly right. Equals the or of x and y. Okay, this is called De Morgan's law. Okay. As I said, discoveries came easier in the 1800s. So you can check that not of and of not x and not y is or of x, y. Okay, and the converse also holds. Not of or of not x and not y is and of x and y. Okay, so which means that you only once you have a not gate, then you only need one of and or, and then you can generate the other one. Okay, in fact, we can even so this shows that and not, for example, is a universal set. In fact, we can even do better than that. We can even have a single gate, which is universal. Anyone know an example? Yeah. The NAND gate, yeah. Okay, so how can we show that NAND is universal? Oh, it's someone else. Yeah. Yep, good. So how do we make a not out of a NAND? Yeah. Yep, exactly. Okay, now how do we make an and out of a NAND? Yep. Yep. Now that we have a not, now we might as well just put that on top of the NAND, and then we've got an and. All right, there we go. Yeah. Yeah. So, okay. So that's a good point. I was assuming here that that you're allowed to just have two wires coming out of the same bit. So this by the way is something that we call fan out. Okay. So yes, we're assuming that you are allowed to copy bits arbitrarily. Okay. That's an assumption that's that we'll make when we're talking about circuits. Interestingly, when we come to quantum computing at the end of the course and we talk about quantum circuits, we will find that we need to drop that assumption. Okay? In the quantum world, you're not allowed to copy things arbitrarily. Okay? But in the classical bits, sure. You've heard that you've all heard from Stallman, right? That information wants to be free, right? Or it can be it wants to be copied all over the place. Okay, so there you go. All right, so now we know that the NAND gate is universal, and in fact, if we did this construction, with NAND gates only, the size of the circuit would change by only a constant factor, right? Because every and an or and not gate can be represented by some constant number of NAND gates, like 2 or 3 of them. Okay, so we can represent any Boolean function of n bits using at most n times 2 to the n, or O of n times 2 to the n NAND gates. Okay, but now let's come back to the question: is that optimal? Could we improve that? Could there be a way that we could represent any n-bit Boolean function using only, let's say, n squared NAND gates? That would be right. That would be awesome if we could do that, right? Yeah.
So I forget what the name of it was. There was some sort of table, but basically, if you were to have anything where they have
So, all right. I mean, no, it's yeah, it's worth thinking about. But yeah.
I don't know what the exact instructions are. If you could take the logical expression
Mm-hmm.
of the circuit
Mm-hmm.
and simplify it
Yep.
to the smallest
Mm-hmm.
gate.
Mm-hmm. Yeah, so there are very often, tricks for simplifying circuits, building them out of a smaller number of gates, right? Sometimes, you might come up with a naive way of building a circuit. Like for example, let's say you wanted to compute the majority of n bits, right? You could do it this way, right? You could do it using this truth table construction, but that would be a wildly inefficient way to do it, right? In fact, it is possible to create a circuit that computes the majority of among n bits using only about n times log n gates. Okay, I think maybe even a linear number of gates. Okay, but I'll check how hard it is, and if it's not too hard, I'll put it on the P set. Okay, but but there are many cases where you can express something interesting, complicated using a circuit which is actually quite small, right? Or you could start out with a complicated circuit and then simplify it using Carnot maps or whatever you call them. Okay, but now with our sort of 6045 goggles, we want to the question we want to ask is it possible that you could always do that, or is there some obstruction that's going to require some Boolean functions to always need circuits of exponential size? Okay. And so one way that we could approach that question is that we could just try to come up with specific examples of functions that we think require exponential size circuits, right? Like one good candidate would be if we took a Boolean function that encoded an NP-complete problem. Okay, I haven't told you yet what NP-complete problems are, but for example, let's say that these zeros and ones, encoded whether there was an edge or there wasn't an edge between various pairs of vertices in a graph, and now the Boolean function will be 1 if that graph contains a Hamilton cycle, which is a path, a tour that visits each vertex exactly once. Right? That's a famous, NP-complete problem. It's one for which we don't, know any efficient algorithm to solve it. And so you might say that maybe it should also require circuits of exponential size. In fact, the question of, finding a specific problem like that one, where you can prove that it requires exponential size circuits, is very, very closely related to the P versus NP question, okay, which we're going to talk about later in the course. And we'll see exactly how this question is related to P versus NP. Okay, but suffice it to say for now that it's also an insanely hard question. Okay, we hope someday, if civilization lasts long enough, that we'll be able to prove that this Hamilton cycle function requires circuits of exponential size. Okay, but right now, the best that we can prove for such functions is that they require circuits of size at least 3n or something, right? We can prove that they require circuits. We can't even prove that such functions require circuits of more than linear size. Okay, is what I'm saying, right? And people just fight about the exact, to improve the exact constant, in front of the n. Okay, that's the best that people can do today, right? It's kind of pathetic. Okay, so, but we will sort of see later in the course why it's such a profoundly difficult mathematical problem to, take a particular function that you care about and then prove that, let's say, there is no circuit of, linear size or of n squared size or something that could possibly compute that function, right? Very, very hard to prove that kind of statement, okay? Okay, but in 1949, Claude Shannon did something, which is sort of obvious in retrospect, but which is an amazing sort of shift of perspective. Okay, what he said is that it's true, I can't give you a single example of a Boolean function that requires gigantic circuits. Okay, but I can prove that such functions exist. Okay, and not only that, I can prove that almost every function requires gigantic circuits. Okay, even though I don't have a single example of one. Okay, so how did he do that? Well, he used what mathematicians know as a counting argument. Okay, so the basic idea here is that we're just going to count how many different Boolean functions are there of n bits, and then we're going to count how many different circuits are there of a small size, right? And then we're going to use the following observation that it's possible that two completely different circuits could represent the same function, right? This can certainly happen. Okay, but it never happens that the same circuit represents two different functions, right? Once you've specified a circuit, a circuit is just a way of specifying the function, right? So each circuit can represent one and only one Boolean function, okay? Which means that if there's a gigantic set of possible Boolean functions, you should think of this oval as gigantic, okay? And there's only a small number of circuits, of a small size that can, that there can possibly be, then there just aren't enough circuits to go around, right? Which means that most of these functions, even if we can't give examples, we know that sort of the chocolate chips fail to cover the cookie. Okay, most of the functions that are out there have to fail to be represented by any small circuit, just because there aren't enough of them. Okay, so let's do the calculation and let's see exactly what comes out of it. Okay, so the first thing we have to ask is how many different Boolean functions are there that take n bits of input? Anyone? Yeah. Yeah, exactly. So some some years when I ask this question, I get a guess of 2 to the n, right? And 2 to the n is big, but it's not nearly big enough for what we're talking about here. Okay, because the question here is how many different truth tables are there, right? Each Boolean function corresponds to one truth table. Right, and just a single truth table already takes 2 to the n bits to specify. Okay, because you've got 2 to the n different inputs, and for each one, you choose whether the output is a 0 or a 1. In order to specify a Boolean function, right? So you've got 2 to the n choices to make to specify one function. Okay, which means that if we're interested in the total number of Boolean functions, then this is actually 2 to the n power. Okay, this is doubly exponential. All right, so now the next question that we need to ask is how many Boolean circuits are there of size at most s? Okay, and to clarify, let's say that we're talking about circuits that are over n input bits, x1 up to xn, and let's say that these are circuits of NAND gates only, okay? Because we've already seen that NAND is universal. Okay, so we don't have to worry about different types of gates. Okay, we're just asking sort of how many different ways are there to string together a circuit of at most s NAND gates. In order to create a Boolean circuit on n input bits. Okay, and once again, we don't really care about the exact number, right? The exact number may be something complicated and messy and depend on what we, identify as being equal to what. Okay, all I really want here is an upper bound. I want a reasonable upper bound on the number. So, okay, this is all available on the syllabus, this information, okay? So all right, so let's just do this by plunking down gates one at a time, right? How many choices are there for how to put just say a single NAND gate, for these n bits? Well, yeah, it's basically n choose 2, except that let's say we allow, the NAND gate could take the same 2 bits as input, so then it's actually n choose 2 plus n. Okay, but between friends, let's just say it's n squared. I mean, seriously, right? It's just a factor of 2 difference anyway. Okay, so all right, and now now how many choices are there for the second NAND gate that we put down? So let me draw the first one. How many choices are there for the second NAND gate? Yeah, one more. Well, okay, let's say n plus 1 squared, right? Because now we've got the new NAND gate could take any of these 2 guys as input, but it could also take the output of the first NAND gate as input, right? So there's really n plus 1 choices here for each of for each of the 2 wires, for both of the wires. Okay, so we've got n plus 1 squared choices for the second NAND gate. How about for the third NAND gate? N plus 2 squared. Now we've got 2 NAND gates, in the house, so we can, the output of either of those can be the input to our third NAND gate. Okay, and for the next one, we've got n plus 3 squared, and so forth. Let's say all the way up to n plus s minus 1 squared, right? But again, I don't like messy expressions. Okay, so between friends, let's just say that this thing is at most, let's just say that each of these guys is at any rate at most n plus s, right? So this thing is really at most n plus s to the 2s, right? There we go. Okay. So now what we've got is that there are at most n plus s to the 2s different circuits of NAND gates of size s. Okay, and actually we were interested in circuits of size at most s. But the truth is the ones of size less than s will just add such an infinitesimal amount to this that I'm not going to worry about it. Okay, it's going to be a geometric series, right, or more than geometric series actually, and it's going to be totally dominated by the last term in the series. All right, so let's just worry about that. Okay, and now we know that if s is big enough that every Boolean function of size n can be represented by a circuit of size s, then this needs to be greater than or equal to what? Anyone? Two to the n, right? This needs to be big enough that there can be a circuit for every Boolean function of size n. Okay, so now all that's left to do is to solve this for s. Okay, so how can we solve this? Anyone? Well, anytime you've got stuff in the exponent, you want to get at it, the first step is to log both sides, right? So there, we have this. Now, how do we solve this thing for s? Anyway, well, once again, if you fixate on finding an exact solution, there's not going to be a closed form solution, for S in terms of n, that, involving sort of any functions that you've ever seen before. Okay, so let's just forget about getting an exact solution, right? We basically, this n is actually going to be like totally unimportant because S is going to be so much bigger than n anyhow. This factor of 2 is also going to be, unimportant in the scheme of things. Okay, so really what we want to know is like how big does S have to be for S log S to exceed 2 to the n? Anyone want to give me an estimate? I mean, let's say that S was 2 to the n. Then what would S log S be? 2 to the n times n. So even if S was all the way at the top, if S was 2 to the n, we've only sort of overshot the target by a little bit. We've gotten only up to 2 to the n times n. Okay, so maybe we should scale back S a little bit. Anyone have a guess for what S should be to satisfy this? Okay, well, it turns out that the S that will satisfy this is going to be about 2 to the n divided by n. Okay, and the best way to come up with this is just to play around with things until you find something that works. Okay, or just you have experience with similar things. Okay, so like but here's a way of once I've told it to you, here's a way of checking it, right? We can just say what's 2 to the n over n times log of 2 to the n over n. Right? Well, log of 2 to the n over n is what, anyone? It's log of 2 to the n minus log of n, right? Let's say that all our logs are base 2, just to, be friendly. All right, so that's like n minus log n. Right? Okay, so this minus log n is just some little piece of crud. Okay, that's just, not going to affect anything. Basically, we have here 2 to the n over n times n. It's about 2 to the n. That's what we want. Okay? So, I'm trying to inculcate you in the ways of bounding. Okay? Yes? Okay, good. Yep.
Mm-hmm. The n squared, n plus 1 squared, that thing, and turned it into n plus s.
Yeah, that's right. Okay, so actually you ask a very good question. So here's the thing: like if this were physics, right, then I could just do a whole long chain of this is approximately equal to that, is approximately equal to that, and just neglecting the lower order terms that we know, don't really matter, except sometimes they do, but right. Okay. If we were, if this were, say, a calculus course, right, then we would only need, we want to be much more careful. We would want a whole chain of equalities and just know what's exactly equal to what. Okay. In theoretical computer science, we mostly want bounds. Okay, so the reason why we're allowed to be, this fast and loose is that, our final answer that we want is only a big O or a big omega. Okay, so we know that, we are, this is an exactly true statement. This expression is at most this expression, right? I have upper bounded it. Okay, I know that all I need for the number of circuits is an upper bound. And so, I'm not allowed to err at all in the opposite direction, right? I'm not allowed to undercount, the number of circuits even by 1, but I'm allowed to overcount by as much as I want because, all I'm going for is an upper bound here, right? And, and if I make a mistake, if I overcount by too much, that will just mean that the bound that I get at the end will be maybe weaker than I'd like it to be, but it won't be false, right? Okay, so here, I claim, so if you want to be precise about it, the claim would be that there is some constant multiple of 2 to the n over n that sort of oversatisfies this this inequality, right? For which s times log s is more than 2 to the n, and there is some other constant multiple of 2 to the n over n for which s log s is less than 2 to the n. Okay, so therefore, whatever we say about the s that satisfies this, it is some constant multiple of 2 to the n over n. Right? That would be the formal statement to make here. Okay, or this is what we want to say. Okay, s is big theta of 2 to the n over n. Okay, now, well, okay, that's the, or at least the solution to this equation is big theta of 2 to the n over n. Okay, the conclusion of the argument is that the number of gates that we need to represent an arbitrary Boolean function is big omega of 2 to the n over n, meaning so from this argument, we conclude that to represent an arbitrary Boolean function of n bits, you need at least on the order of 2 to the n over n NAND gates. Okay? Maybe it's more than that, right? What was the upper bound we had? Well, you can see that the upper and lower bounds here are off by a little bit, right? The upper bound that we got was 2 to the n times n. Okay? The lower bound was 2 to the n divided by n. So they're off by a factor of n squared, right? But they're pretty close in the scheme of things, right? So you could say, we have shown that you can represent any Boolean function with about 2 to the n gates, and in fact, you need 2 to the n, about 2 to the n gates to represent an arbitrary Boolean function. Okay, now you might wonder about the exact answer. So if you invest enough work, in fact, it can be proven. Was proven by various Russians in the 1960s that this is tight. Okay, that in fact you can represent, so you can improve the construction. The construction is the thing that has to improve here. You can give a better, an optimized construction that represents any Boolean function of n bits using only about 2 to the n divided by n gates. Okay, and that's a considerable amount of work to do it, and not all that interesting either. So we won't, so I'm not going to cover it here. Okay, but counting arguments have the remarkable property that that often not only do they give you an answer, they give you the tight answer. They give you exactly the right answer, even though they didn't give you a single example of a Boolean function. We still don't have a single example of a Boolean function that requires an exponential size circuit. We just know that they're almost everywhere. Okay. So if we wanted an explicit example of a Boolean function, like if you wanted to program your computer to just come up with, deterministically a Boolean function that requires exponential size circuits, how could you do that, anyone? Can anyone suggest a way to do that? Well, there's a really, really stupid way to do it, okay? But amazingly, this stupid way is sort of almost the best that we know today after 60 years of research on these sorts of questions. Okay. And the way is this. So we can list all the possible truth tables of n bits, right? There are 2 to the n of them, okay? And we can list them in what we call lexicographic order. What does lexicographic order mean? It just means that we start with the all 0 string, and then we just keep incrementing by 1, viewing these as integers written in binary, okay? So it's just some standard way of ordering all of the possible truth tables of all the possible Boolean functions. Okay, so these are 3 input functions, so they have 8-bit truth tables which means that there are 256 of these functions. I'm not going to write all 256 of them. Okay, here's the first three. Here. Just for you, I'll write one more. Okay, all right, so we could list them all like this. We could then just go through this list one by one, starting at the left. And for each one, we could just by brute force work out what is the size of the smallest circuit that represents this function, right? We could just you could just program your computer to iterate over all circuits, starting with the smallest, starting with size 1, then size 2, until you find, one that represents your function, and you'll thereby find the size of the smallest circuit for each of these functions. Okay, and now you could program your computer to halt as soon as you get to a function that requires a circuit of size, I don't know, 2 to the n divided by n squared, let's say. Now, we know from Shannon's counting argument that such a function must exist. All right, so since it exists, there must be a first one. So your computer will halt and find it, and which one it finds will be deterministic. There, I've just defined for you an explicit Boolean function that requires exponentially large circuits. Okay, that was a little bit pathetic, right? It's like the thing, usual answer. You ask a mathematician, well, where am I? You're lost, right? Just we've answered the question, but without sort of saying anything very useful. Okay, so the big challenge here is to come up with more natural examples of Boolean functions that still provably require exponential size circuits. Okay, so so now you might say we've shown in any case that Boolean circuits are universal, right? You can use them to represent any Boolean function whatsoever. So in that sense, why isn't this just the model of computation that we want to use for the rest of the course? What are the drawbacks of circuits? What are the limitations of circuits? What can circuits not do? Does anyone see what aspects of the computers that we actually use are sort of missing in circuits? Memory, yeah. Yeah, that's a big one. That's and that's actually the one I want to focus on here. The Okay, so we like to distinguish between uniform and non-uniform models of computation. So circuits are an example of a non-uniform model, which means that sort of you need a different circuit for every input size. Even if you've invested lots and lots of work to design the perfect circuit for computing the majority function of 100 bits. Right? Well, that's great. You pat yourself on the back, and then someone hands you an input, of 101 bits, and asks you to take its majority. Right? Your circuit is completely useless. Right? You might as well just trash it and just start over from the beginning, designing a circuit for 101, bit inputs. Okay, so that's not very useful, right? We would like to be able to design, a single program that can handle inputs of arbitrary size. And in particular, we would like inputs that can, we would like programs that can handle, inputs that are much larger than themselves, right? Like the total code base of Google, for example, is pretty large, okay? But it's a speck, it's nothing compared to the entire size of the internet, right? Which is the thing that it sort of takes as its input. Okay, so we'd like programs, that can handle inputs that are much larger than themselves, and circuits don't do that, right? A circuit is, sort of, if it's a circuit that acts on all n bits of the input, then it has size at least n, right? And so it's at least as big as the input that it's operating on. Okay, so we want to move over to sort of we want to move over to uniform models. A uniform model is one where you've got just a single program and it can handle, an input of any size. Okay, but we want to get our feet wet with this, so we're going to start out with maybe the simplest type of uniform computer that there is, and this is what we call a finite automaton. Okay, now you can think of a finite automaton as basically just a very, very hobbled computer that can only read its input in one direction. Okay, it can only read its input from left to right, and just if it's a Hebrew or Arabic finite automaton from right to left. Okay, either way, but it can only remember a little bit about what it's seen so far. Okay. So the basic idea is, and there's actually a more modern name for these, which is streaming algorithms. Okay, so there's actually been like a resurgence of interest in these kinds of things recently because of big data, because you actually want sort of a program that can just make a single pass through massive number of terabytes of data, right? You don't have time to make multiple passes and just learn something interesting even while it's doing that. Okay, so even the sort of most rudimentary models of computation that we're going to see in this course, they still have applications today. Okay, but anyway, the idea is that you get this sort of stream of bits, and you can read it in one direction. Okay, you're some device, and your construction, the construction of the device, might be complicated. It might have all kinds of components to it. But we want to abstract away the details of the construction of the device. And what we want to say is that whatever this device is doing, it has the property that sort of whatever it has remembered about the bits that it's seen so far can be encapsulated in a single object that's called the state. Okay, so in other words, there is a finite number of different configurations of different internal configurations that this machine can have at a given point in time. For example, it could have a switch, which is either on or off, right? That would be a two-state automaton. It could have two switches, which are each independently either on or off. That would be a four-state automaton. Okay, but at any rate, it has a finite number of possible states. That's the key limitation here. Why is that an important limitation, anyone? Well, you could say it's first of all, it's important for a physical reason, right? How on earth do you build a device that has infinitely many states? Okay, it would need an infinite amount of memory. Okay, but secondly, if we allowed an infinite number of states, that would just completely trivialize what we're talking about, because we could then just say you're going to read these bits from left to right, and your state just consists of a record of all the bits that you've seen. Okay, so you're just like a hungry hippo or something, right? You're just gobbling up these bits, okay, and and then you see all the bits, and it's trivial. Okay, so we want to capture the fact that this machine only has a limited ability to remember what it's seen, right? It's going to be reading in very, very long inputs, but it only has a small memory to remember sort of the most important facts about those inputs, right? Like it's studying for the test. Okay, it's skimming for at the end there's going to be a final exam, and it wants to only retain the most important material from this string. Okay, so let's since it'll only take 2 minutes or so, let's just do an example of a finite automaton. I would like a finite automaton that just checks whether there are any 1 bits in this string. How do I? Okay, so the automaton, as I said, it has some finite number of possible states. Let's call the states like A and B. it also has, one of the states we designate as a start state. Okay, let me designate A as the start state here. Okay, and some of the states are accepting states and others are rejecting states. Okay, so I'm going to call B an accepting state. It's a state where it accepts the string, and I'm going to call A a rejecting state. Okay, and now what we can do is we can define transitions among these states. So this is a finite automaton that reads a string of zeros and ones. So we say that its alphabet, the set of symbols that it can read, and which is denoted by sigma, consists of 0 and 1. Okay, and then the key thing that you do in specifying a finite automaton is that you define a function that takes, so let's say that S is the set of states. In this case, it's A and B. Right? And then what you do is you define a function that maps a state and an alphabet symbol to a new state. This is called the transition function of the finite automaton. Okay, so you define a function that says, given what state you're in now and given what symbol you're reading, here is the new state that you're going to go to, and then you go and read the next symbol. Okay, so we can represent such a function using arrows. So so now I said I want a finite automaton that's going to accept if and only if there's any 1 in my string. So what arrows should I draw from this A state? Anyway, huh? If I'm in state A and I read a 0, what should I do? Stay in state A. If I'm in state A and I read a 1, what should I do? Go to state B. Yeah, because now I know that I can accept. Okay, if I'm in state B and I read a 0, what should I do? Stay in B. If I'm in state B and I read a 1, what should I do? Stay in B. There we go, our first finite automaton. Okay, so next Tuesday we'll see a couple more examples. We'll prove some theorems about what finite automata can do and what they can't do, and what else they're equivalent to. And P set 1 should be out this weekend. Okay. Yep.